Hi, this video covers prediction using regression equation to make those predictions, and we'll also be using DESMOS. So if you'll recall from a previous video, we talked about data involving house prices and house size. The predictor variable was the house size, also known as the independent variable, and the dependent variable, or the response variable, was the house selling price. So we used the data points to create a regression equation, and that equation was y equals 0.0992x plus 160.194. And so we can use that equation because that equation is showing a relationship. So we can use that relationship to show to make predictions. So based off of the trends that that we created that equation from. So when they say predict the price of a home with 2,700 square feet, so what you have to remember is that X represented the size of the house in square feet, and Y represented the selling price in thousands of dollars. So here they're giving us the size of a house, and they're asking us to predict the price. So they're giving us the X, and they're asking us to predict the Y. So I'm going to start with the equation. Y equals 0.0992x. And instead of X, I'm going to fill that in with the value they're saying X is, plus 160.194. So if I sub in 2,700 for X, we can calculate a Y. So we'll go to DESMOS and X out here, and we will do 0.0992 times 2,700 plus 160.194. And you can see that we get 428.034, and this is in thousands of dollars. So we get 428.034, but this is in thousands of dollars. All right, so what I can do is I can take this number, 428.034, and multiply it, because that's how many thousands there are. Multiply that times 1,000, and you get 428,034. Okay, so again, the X was the size of the house, the Y was the cost of the house. We're substituting in the 2,700, and we are solving. So we substituted the 2,700, and we put it right there in for X. We're going to do the same thing in this next one. Predict the price of the home with 4,500 square feet. So again, we start off with our regression equation, and instead of X, put parentheses, and then inside those parentheses, we're going to fill that in with 4,500, and then we're going to go to DESMOS. And so I'm going to cheat. I'm going to go up here to box 1, and I'm going to change what was into parentheses to 4,500. And we get 606,594. Which, if you multiplied it by 1,000, that'd be $606,595 for a house that is 4,500 square feet. Now, is that exactly what it's going to cost? We are estimating. We are predicting, but it doesn't mean that it's going to be that exact cost. All right, so here's some things. interpreting the predicted value of y. So which of the answers do you think will be a better prediction? So do you think it's a better prediction off of the 2700 or the 4500? And so this requires us to kind of go back and look at the data from the original problem. Okay, in the original problem, here were the data points. And so what I want you to do is look on the left-hand side. Look at the sizes. The sizes went from 2,521 all the way up to 3,198. So the regression equation is based off of the values that you see here. So it's based on values that are in a range from 2,500-ish to 3,198. So if you'll look at the numbers we plugged in here, oops, I clicked on the wrong thing. Let me find it. All right, so if you look here, we plugged in 2,700 and 4,500. 2,700 fell within the boundaries of those points that we had in that data set, whereas 4,500 falls outside of that. So basically, our equation only represents the patterns that we saw between that 2,500 and the 3,198. Outside of that, we don't know what would happen. Right? So that brings us to a couple of vocabulary words. But basically, when we plugged in the 2700, that was called interpolation because it made a prediction for the data point inside the range of data. Okay. And then when we plugged in 4,500, that was called extrapolation because it made a prediction for a data point outside of the data range. So interpolation is when you make a data prediction based off of a number inside the data range, and extrapolation is when you make a prediction based off a data point outside of the range of data. And so what's important to note here is that interpolations are more reliable than extrapolations. So we would consider the first answer, this one here, we would consider this reliable because this number here, 2,700, falls within the original data range that our equation is based off of. Because this one falls outside of that, that's called extrapolation. And again, it's not as reliable as this one. So we would consider this answer reliable, but we would consider this one that used the number outside of the range unreliable. The other thing you can check is whether or not your answer seems reasonable or not. So does it seem reasonable to have a house that costs $428,034? Yes. Is it reasonable for a 4,500 square foot house to cost $606,594? I would say that is reasonable. Now, again, it's not reliable because that 4,500 fell outside of the original data range, but the answer does seem reasonable. So reasonable meaning kind of doesn't make sense. Would it make sense for that answer to be the answer? So let's predict the data on the student's third test. If you'll recall, this was the equation we got from the very last problem we did in the last video. The data of student's third test and final exam led to the following equation for the regression line. What final exam score would you predict for a student who scored a 60? So why don't you, so just recall real quick, X was the third exam score and Y is the final exam score. So why don't you pause the video and try to work this out, and then when you come back, we will talk about what the answer should be. Okay, I'm going to rewrite the equation. And instead of putting X, I'm going to put what we're saying X equals the third test is the x. So we're subbing in 60 right here. So if you did this calculation, you should get 116.107, which if I recall is definitely possible. It is possible because it was out of a score. The final exam was out of 200. And real quick, I just wanted to pull up the original data set just to see if this was a reliable solution. And if you look at it, the range goes from, I believe for the x's, it goes from 65 all the way up to maybe 70, 75, somewhere in there. I don't see anything below a 65. So, but we just plugged in 60. So because it falls outside of that, this would be considered extrapolation, and it's not reliable. But is it reasonable? I would say it is reasonable, and the reason is because the final exam scores are out of 200. So you could definitely make a 116.107. All right. So let's move on. A couple more examples. Let's do this one. At the final exam in a statistics class, the professor asks each student to indicate how many hours he or she studied for the exam. After grading the exam, the professor computes the regression equation for predicting the final exam score from the number of hours studied. And the equation is y equals 5x plus 50. Antoine studied for 6 hours. What do you predict his exam score to be? And Michaela made an 84 on her exam. How many hours would you predict that she studied? So first, I'm going to let you know that I'm just giving you the equation here. You do not have access to what the actual study hours or the scores were. So you can't decide whether this is extrapolation or interpolation, right? But we do want to do the predictions. In this case, there's one where we're predicting the y based off x, but there's another one where we're predicting the x based off of the y. So we definitely want to do these together. So for Antoine, so let's just write up here what each one represents. X represents the hours studied, and y represents the score on the test. Okay, so once we've identified that, Antoine studied for 6 hours. So which one did they give us? They gave us the x. So we're going to say y equals 5x plus 50. And instead of x, we are going to put in 6 hours. So you can enter that in DESMOS straight across, or we can just add it together here. So that'd be 30 plus 50. So that would be an 80. So Antoine, we would predict, based off of his 6 hours of study, we would predict that he made an 80. All right. Now, the next one, Michaela, we're giving you her score, and we're predicting the number of hours. So we're actually giving you the y. This is the y, and we're predicting the x. Okay, so since we know what the x and the y are, we're going to start with our y equals 5x plus 50, and we're going to replace the y with 84. And we're kind of going backwards here. We're trying to get the x by itself. What I like to do is draw a line down the equal sign and circle the number I'm trying to get by itself. We're going to start unpacking everything. So you look and see what is happening with the x. We want to get x by itself, because once we get it by itself, we'll know what it equals to make the equation true. So we'll figure out how many hours we need to make a score of 84. So we always get rid of what's being added first. Well, you can get rid of what's being multiplied, but it is a little bit more complicated if you do it that way. So we're going to undo the adding 50 by doing the opposite, which is subtracting 50. And then the golden rule of equations is what you do to one side, you do to the other. So when we do 84 minus 50, we will get 34. On the right-hand side, we have 5x. And we're still trying to figure out what this x equals. So undoing the 5, this is 5 times x. So to undo that, that's 5x divided by 5. And what you do to one side, you do to the other. So we're going to divide both sides by 5. And then we're going to get 6.8 equals x. So the number of hours that that Michaela would have studied based off of her score, we would predict that to be 6.8 hours. Next, we're going to talk about interpreting slope. So what does the slope mean? So real quick, quick review, y equals mx plus b. That slope-intercept form, the m is considered the slope. And if you will recall, hopefully you've learned this in the past, that slope, another way to look at slope is that it's the rise over the run, which is the same as your change in y over your change in x. And so because we're dealing with y and x in context, we need to think about the units for each. So when interpreting slope, we need to think of the y units and the x units. So in the previous example, our slope was 5. 5 was our slope. Y equals mx plus b. 5 is the slope. But our units, remember the x was hours. The y was your score on the test, right? So, going back to this next slide here, we would say that the score would improve by 5 points for every hour. So we always do the rise is the y, the run is the x. So think of the units. So we could say that the score increases by 5 points per hour of study. So think y units per x units when you're interpreting the slope. So slope is how it's changing over how the y is changing over how the x is changing. And the over, the fraction bar, we can replace with the word per in many cases. So again, 5 would be the number of points that your score changes per hour of study. So moving on to the y-intercept. Y-intercept is the b. So when we have y equals mx plus b, it is the b in the equation. And it's where the equation crosses the y-axis. So if we had a graph, it would be where it would cross that y-axis right there. And this is where the x is equal to 0. So since it's where the x equals 0, we can say that that's where basically the starting value. So before x starts increasing or decreasing, that's where we're starting, usually anyway, when we're dealing with problems in context. And it also, whatever the y-intercept is, because it is a y value, specifically where the x is 0, it will have y units. So when we interpret it mathematically, again, it's the point where the x value is 0, but you have to figure out realistically if that's going to be meaningful or not. Because sometimes having a value of 0 for x isn't going to make sense depending on what your values represent. So you always want to check that to see if the y-intercept is meaningful to the problem or if it's just something that we have to mathematically make the equation work. If only positive values or negative values are meaningful for x, then y-intercept is not meaningful in context. So meaning if 0 doesn't make sense to be x, then whatever the y is in that location isn't going to make sense either. It's just there to make the equation work. So things to think about. So let's look at these. For each of the following scenarios, decide whether or not the y-intercept is meaningful in context. So the house price example. So for the house price example, it was y equals 0.099, I think it was 2x plus, what was it, 160.194. Okay, so this has a y value. That's when the x is 0. And so the x was the size. So this is when the size of the house is 0. The price is 160,194, because remember that's in thousands of dollars. Now, the price seems, that seems like a price of obviously a cheaper house, but the size can't be 0. So this does not make sense in context of the problem, because you can't have a house that is size 0. The test score example. So in that case, the equation was somewhere along the lines of y equals 4.827x minus 173.513. In this case, we have a y-intercept of negative 173.513. That is the final exam score. And that is when the x, which is the third exam score, equals 0. Well, you can definitely have a 0 on an exam score, right? But can you have a negative exam score? Thankfully, that is a no. That would be really bad, right? So does this make sense in context of the problem? Again, a negative final exam score is not going to make sense. So we're going to say no there. The regression equation is y equals 1.98 plus 0.039x. Notice they flip-flop the m and the b. All right, the m is the 0.039 and the b is the 1.98. X is the temperature in a freezer in degrees, and y is the time it takes to freeze. So the y-intercept in this case is 1.98. So it takes 1.98. They don't specify whether it's minutes or seconds or hours. So let's say this is, I don't know, minutes. So 1.98 minutes to freeze when it is 0 degrees Fahrenheit. I would say that does make sense. I think that does make sense in context of the problem. What about this one? A regression equation of y equals negative 13.586 plus 0.4340x, where x represents the age of an elementary schooler, and y is the score on a standardized test. So the score on the test is negative 0.13586 when the student is age 0. That would be a no. Because 0 is how old you are when you're born. So that doesn't make sense either. So the only one in this case that made sense was this third one. So let's look at a couple of these using slope and y-intercept. Ethan repairs household appliances like dishwashers and refrigerators. For each visit, he charges $25 plus $20 per hour of work. A linear equation that represents the total amount of money Ethan earns per visit is 25 plus 20x. What are the independent and dependent variables, and what is the y-intercept and the slope? So the independent variable, I'm going to write I for independent, is usually your x. And in this case, it is the number of hours worked. And then your dependent variable is usually your y. In this case, it's the amount charged. And it's in dollars. So our slope is usually the number in front of x. So that's 20, right? So it's 20. And remember, we use units. So y units would be $20 per hour worked. So we're going to charge, it's going to, the amount charged is going to, it's a positive, so it's an increase, $20 for every hour worked. Now your B is your 25, and that's your, basically it's your starting value. So that's the amount that they charge no matter what. So they're going to charge $25 just to visit and then add on $20 for every hour of work. So 25 is the starting value. 20 is the slope. That's the amount that is increasing per hour worked. All right, so let's look at example 6. Woo, we've got lots of numbers in here. It says compute the regression equation. The following table lists the heights in inches and weights in pounds of 14 NFL quarterbacks in 2009 season. So why don't you guys pause the video and then enter these data into DESMOS or in our Guru, whichever one you're using, and calculate the regression equation and R. And then when you come back, unpause the video and you can see if you're correct. Okay, so just to review, you're coming back to check what those answers would be. You would have gone to DESMOS, hit the plus sign, chose table, entered the heights in the X column, the weights in the Y column, and then underneath that in box 2, you would type in Y1 tilde MX1 plus B. It would give you an M and a B to fill in. So the M, I believe, is 3.272. X plus B is negative. So I'm going to change that plus sign to a minus. 20.021. So hopefully you got the same thing. If you look at the R is 0.5628. Ooh, so it's not really super close to 1. It's not super close to 0 either. So I would say this is definitely a positive correlation, but it is it's more moderate than a strong correlation. So what this is saying is this is showing the relationship between to predict weight based off of height. So it says interpret the slope. So which number is the slope? The slope, you will recall, is the number in front of x. So that's 3.272 x. It's positive, so it's increasing. If it's positive, it's increasing. If it's negative, it's decreasing. And again, it's the rate of change. It's showing how it's changing. So it's changing by increasing 3.72 Y units, and the Y is weight. So I'm guessing this is pounds per, the height units would be inches. So for every inch we go up, you go up 3.272 pounds. Is it possible to interpret the Y-intercept? So the Y-intercept is negative 20.021. This is your weight. This is pounds. And this is when the X is 0, and the X is your height in inches. And I would say this is no. It doesn't make sense because 1, you can't be 0 pounds, and 2, 1, you can't be 0 inches, and 2, you can't be negative 20 pounds. So it is not making sense here. And it says predict the weight of quarterback who is 74.5 inches. So we're going to take the equation y equals 3.272x minus 20.021, and we're going to sub in 74.5. And when we do that, I believe we get 223.74 pounds. And if you go back to the original data sets, 74.5 does fall within that range. So this would be a reliable solution because it's interpolation, and I would say 223 pounds is reasonable for a weight. So then the last question, I think it's the last question, yeah. Does Tom Brady weigh more or less than the weight predicted by the regression line based on his height? So what you want to do is you want to go back to Tom Brady. Tom Brady is 76 inches, and he weighs 225 pounds. But we're trying to see if the equation using the 76 will actually predict his real weight. So we're going to take the original equation, y equals 3.272 times x minus 20.021, and we're going to replace this with Tom Brady's real height, which is 76. And when we do that, we get y equals 228.651. Now, how much does he really weigh? He really weighs 225. So, we were close though. This was only off by what, 3.5 pounds. So the Tom Brady actually weighs 3.65 pounds less. So again, this is a prediction, it's an estimation. It's not necessarily going to be exactly accurate. All right, so I have another example, blood pressures. So this, I just want to let you know, this was too long to do one table. So this is only half of the data points. Here's the other half. So systolic is the top number in blood pressure, and then diastolic is the bottom number in blood pressure. So you're going to enter all of the systolics in your X, and you're going to enter all the diastolics in your Y for these 16 adults. You're going to put in 16 points, and then you're going to calculate the R and the regression equation. You're going to try to interpret the Y-intercept as well as the slope, and then you're going to do a couple predictions. So again, hopefully you're following along with the blank notes that I have provided for you on Blackboard. But definitely try this problem. So you can pause the video, try this problem, and then come back and check your answers. Okay, so we ready to check your answers? I got R equals 0.8568. I would say this is strong because it's very close to 1, positive linear correlation, because again, it's close to 1. Do I think it's strong? Yes. Compute the regression equation. The regression equation, I believe, is y equals 0.5748 x plus 9.1828. Interpreting the y-intercept. The y-intercept is the point 0 and then 9.1828, because remember, it's the y-intercept is where the x equals 0. So what are the x units? That's your systolic, and then the diastolic number is that is 9.1828, and I would say no, we can't really interpret that, because if you have 0 as your top number, that's bad. It's really, really bad. I don't think you'd be alive. So I would say the y-intercept doesn't make sense, but the slope, it's positive. The slope is a positive 0.5748. So what that's telling you is the top number is the y. So the diastolic increases it increases 0.5748 for every systolic point. So if the systolic point goes up by 1, the diastolic is going to increase by 0.5748. So now we're doing a couple of predictions. So if we have Y equals, and they're giving us the systolic blood pressure, which is the X, and they're asking us to predict the Y. So Y equals 0.5748 times X plus 9.1828, and we're subbing in 125 is our top number. Then the bottom number based off of these trends would be 8.103. Oh, I'm sorry. I think I just wrote. Yeah, it's actually not. I wrote 8 and it didn't take. So it's not 8 point. I think it's 81. Oops. 81.0328. But let's just double check to make sure I'm right. So we had 0.5748 times 125 plus 9.1828. Yeah, 81.0328. Yeah, that's what we got there. Okay, predict the systolic pressure for a patient whose diastolic is 92. So I'm going to put 92 here is equal to, for the Y, because they're giving us the diastolic blood pressure, and they're asking us to predict the X. So 92 equals 0.5748X plus 9.1828. So we have to go backwards. So remember, we want to get rid of anything we're adding first. So we'll do the opposite, which is subtract. So subtract 9.1828. So I'm going to do, what is it, 90, 92? 92 minus 9.1828, and we get 82.8172. Equals 0.5748x, and then you want to divide both sides by 0.5748 on both sides. So 82.8172 divided by 0.5748, and we get 144.08. So if the diastolic blood pressure is 92, we could predict the systolic blood pressure to be 144.08. And that is all I have for you. If you have questions, please let me know.